Welcome. We are going to start chapter 3, and I was kind of racking my brain. I can't think of anything kind of administrative to bring up. I'm sure there's stuff I'm forgetting about. I'm sure of it. But let's just get right into chapter 3. Chapter 3. Chapter 3 is called linear regression. What's nice about linear regression is we'll be able to use linear regression concepts for a lot of different, and I dare say, the majority of analyses that you do on your own are going to involve probably linear regression. As soon as you want to predict something, then you'll need probably regression. Right, linear regression typically. So we're going to start in section 3.1, which is on simple linear regression. Now the simple part, the simple is referring to one predictor, so one value of X in this case. Okay, so simple means that there's one predictor, so 1x, and then linear means that it follows a straight line pattern, and then regression is more of a term that we regress y on x, and it's really just looking at the relationship between x and y, but usually we're mostly interested in y, right? How do we predict values of y, the response variable? So typically what we have is that y is going to be, well, technically it's equal to some beta naught plus beta 1 times x plus some error term. So we've talked in general about some f of x, right? Some model f of x plus some error term, and that creates your y. But really what we're going to see is that y is roughly beta naught plus beta 1 x, right? And so what we do, we don't ignore this error term, but for the models that we build, right, this error term, and I might have flubbed it there, but no, I think we're okay. So we just, for the approximation, right, then we have this beta naught plus beta 1 times x. Now this might look familiar, and before I move on, I just want to say that we can say that we're regressing y on x. That's another way that we can describe this relationship, okay? But this might look familiar from probably Stat 230 or, just a straight line, right? The equation of a straight line, y equals mx plus b. Typically we use that setup, okay? And so here, this is the slope, and oh my gosh. No, it's not. It's because I'm used to mx plus b, and whatever's attached to the x, that's the slope. All right, whatever's attached to the x in y equals mx plus b, m is the slope and it's first, but that was my bad. Beta naught is the y-intercept. Just like before, right, we have these population parameters, beta naught, beta 1, they're denoted by Greek letters, which all parameters are, right? So as soon as they're from the population, typically we use Greek letters to denote that. But also, we don't know what these are, right? And so we need estimates for these values. So beta naught and beta 1 are the population parameters. Kind of redundant to say population parameters, but I want to emphasize that we use those terms. population parameter. Okay. So I'll put the population in brackets because it is redundant, but I do want to highlight that the P and the P go together, right? So if we're talking about a parameter, it's understood that it's from the population. Okay. Beta naught and beta 1 are the, and then in brackets population parameters for the y-intercept and the slope. Since we don't know the population, right, we're back at that problem that we've seen a lot in statistics in general, is that, okay, well, we don't know the parameter, so we use some estimate, so some sample statistic, right? Population parameter sample statistic. So we use some estimate, which is a statistic, in its place, and we try to estimate the parameters. Since we can't know the parameters, I mean, unless we have the entire population, which we never do, right? And that's okay, we don't actually need it. So since we can't know the parameters unless we have sampled the entire population. Okay. We estimate the parameters with the statistics. So we use the sample statistics. Okay. So what we do is we start to predict Y values, right? And this is hopefully a little bit of review, but I know towards the end of Stat 230, there's not a ton of time to talk about regression. So you've seen simple linear regression, but not necessarily multiple regression. So we'll start and we'll build up the concepts with simple linear regression, so just one X, and then we'll build it out to multiple regressions. Okay, so so what we'd have is some Y hat is going to be beta naught hat plus beta 1 hat times X. We could use, or you might have seen Y hat equals B0 plus B1X. That's kind of more common to use a B instead of the betas, but here they're using a hat to denote that it's an estimate. Okay. So the hats here using hat to denote an estimate. Right, and that's an estimate based on the sample. Whereas here, Y hat, so context tells us that that's going to be different. Y hat is the predicted value of Y. So now the Y hat, here we're using the hat to denote the predicted value. For now, Y, we're going to assume that Y is a numerical outcome, right? Or a quantitative outcome if you prefer. Yeah. For now, we assume Y is a numerical variable. We can deal with categorical variable. We can deal with non numerical variables, so categorical variables for the response, but we need different techniques for that. So here we are assuming that y is a numerical variable, and we want to predict future values of y. And I'll remove this. And we wish to predict future values of y. Okay. Future does not necessarily mean on a timeline. Okay. What I'm talking about is unseen values, not necessarily in time. Future in this case means unseen. Right, so if I were to collect a completely new random sample, then I would have points that are previously unseen. Okay, so when we talk about beta naught hat and beta 1 hat, generically we'll call those model coefficients, right? And so what we're going to do is we're going to build models based off of our data, right? So we have some sample data and we're going to build some models. Okay. So we call beta naught hat and beta 1 hat model coefficients. Just as a little side note. Now I did cheat and I wanted to bring in some output to talk about, but I don't want it quite yet. So, so I'm just going to add a page here, but that's just because I didn't want to write all those tables out. So got lazy. But those examples, so the example that we're going to use to illustrate these concepts is on advertising, and I think it has 4 variables. In the examples, we will use a data set called advertising, and you can access it through the ISLR library. Is it ISLR or ISLR2 maybe? Anyways, I have to confirm, but you can access it and we can duplicate these models. So that's nice. In the examples, we will use the advertising data from the textbook. Right, you could try to bring it in. And it has, I think, 4 variables. The first one it has is the sales. And I think it's in thousands, but let's just ignore that for now. And then it has the budget for 3 different advertising categories. So we're going to look at the advertising for radio, newspapers, and TV. Okay, and so there's a budget for each of those. And can we use those budgets to predict the amount of sales, right, that we have? Obviously, one key goal would be to optimize how much you spend on each of the 3 categories in order to maximize your sales, right? And so eventually we're going to move to incorporating each of these 3 predictors, right? But for now, we're just going to look at one at a time. So it has the sales, and then it has the budget for TV advertising. And because I can, I'm going to copy, paste, and paste. Was that faster? I'm not so sure. But not TV anymore. Radio and newspaper. Squished in there. Squished in there. I don't know what I said. Okay, and so here, this is our response, right? We're interested in the sales. And then the other three would be our predictors, potential predictors. We use P as the number of predictors or number of potential predictors in general. We're going to refer to P, so that's why I want to bring it up. So in this case, P equals 3. Okay, so we have 3 potential predictors. And we're going to build models and see which model is the best at predicting the sales, right? Given some input of the budget for either TV, radio, or newspaper. Okay. What I've done is I have excluded a lot of the theory from the textbook. There is a lot of theory involved. There are a couple of things that I want to talk about just to check off some points here, but in general, I just want to give you stuff that you can use right away in an applied sense. Okay, but there is a lot of theory and they do talk about it and they do a really good job in the textbook, but I'm cutting it as much as I can. Okay, so what we do is if we have some sort of relationship between X and Y, maybe I have data points and I'll make them a little bit bigger so that they show up here. Right? Maybe we have this kind of relationship and we want to model this relationship. Now, looking at this, if I had to describe it with a shape, I would say, yeah, it looks like a straight line, or it looks like I could summarize it with a straight line. Now, this is where we get into, okay, we're going to focus on linear regression. So either it is a straight line or we force it into some sort of straight line. That's an option too. Just makes it a little bit trickier to deal with. But what we're assuming is that we can model with a straight line. And so what we get here is don't need that thick of a line here. So we say that Y hat is beta 0 hat or beta naught hat, beta 1 hat, X. Okay. Now you might remember the distance from a point, so let's say this point here, at the same value of X, okay, that's supposed to be straight up and down. I know it's not, but this distance from the actual Y, okay, so here, this is going to map back to some Y value. I want to call it YI, but it's a particular Y. So in this case, no. The distance between the actual Y and the predicted value of Y at the same point of X, that's your residual. So we call it the residual, or what we could also call it is we could call it there. We could call it the error if you want, okay? And so the distance between these is called the residual. Oops. So the residual is, so for some I, because each of these points is going to have a residual, it's going to have some distance from the line, right? So EI for the error. Okay. Usually we call it the residual, but it is an error term, right? It's how wrong the model was, right? Where this straight line is the model. So we use E for the error term. Also because a lowercase r is the correlation, right? So we don't want to mix that up. So EI, it sounds like a donkey. So EI is the error term, and it's going to be got a lull. It's going to be the YI, right? So the observed minus the predicted value at that same value of I. Okay, so how I think of it is it's the observed minus the predicted. And that's how I remember what the residual is. Now, the goal is going to be to minimize those residuals. So the tool that we use is called least squares regression. Okay, and so the least squares regression line, which is the method that we use, and it's the most widely used method anyways. So it's the only one we really bother with, but there are others, of course. Others have tried and failed. That's okay. We don't have to feel bad for them. I'm sure they got a PhD out of it, so whatever. So the least squares regression line minimizes the squared residuals. Minimizes the squared residuals. There are other methods, like we could take the absolute value of the residuals instead. But one thing, well, we're taking the squared because we need them to be positive, right? If we're minimizing something, then when we add them all up, we want it to be the smallest value possible. But notice how some of these values, if we take the observed minus the predicted, so if the points are above the line, then I get positive values. And if they're below the line, I get negative residuals. So then when I add those up, just as a fact, it's going to add to 0. So that's not very helpful, because then I would always get 0, right? So then what we do is we square those residuals to say, okay, no, everyone's positive, and then I can minimize it. Okay. And so that's why we square the residuals, is just to have positive values that add up to something, and then we can minimize that. So you could take the absolute value, but just as a side note, the reason we square the residuals is because a residual that's twice as large is usually more than twice as bad, right? So if it's twice as large and then we square that, then all of a sudden it's 4 times as bad, right? And so we want to capture that, okay, there's some baddies in there, and we need to adjust for those. Okay. We square the residuals because typically a residual that's twice as large is more than twice as bad. A residual that is twice as large is usually more than twice as bad. Is more than twice as bad. Okay, bad for the model. I'll say that, for the model. Okay. Yeah, hey, that's a good one. Yeah, so what we do is we say, we just kind of, yeah, so the magnifying glass, I really like that. It just kind of blows things up and says, okay, if you're close to the line, then you're not a problem, then this line is good, right? But if you're far away from the line, then I want to magnify that and say, okay, actually that's more than twice as bad, right? Or something like that. So you kind of move them out further and make them kind of harder to catch. Okay. So what we're doing is, and I had a little note here that I wanted to, yeah, to add in here. Yeah, so when we take the absolute value, all that would happen here, for example, is that these would just be replicated on the other side, but then the distance is just the distance, and so it just stays the same. And that is a way that we can deal with this, right? And we can still minimize those distances, but by squaring it, we get a little bit more information, okay? Because what we find is that the line actually needs to get pulled towards any extreme values, right? And so then we need to account for that in our least squares regression line. Okay. So that's why we use the squared value. Okay. All right. So what we're doing is we minimize, well, we don't, software does, but the method that we're using is we fit the model to minimize the sum of the residuals squared, okay? And often I'll get lazy if it's kind of obvious that you're summing over all the possible values and the sample size is n generically, right? So here, often I'll kind of I equals 1 to n, but that's understood. So often I won't even put those on the summation, and it's fine if you do too, as long as it's obvious that I is summing from 1 to n, right? You're allowed to do that. Sometimes I even get lazy and I don't even have that I there. That's bad. Should probably have that I to show that it changes over all the residuals. But here it's obvious because there's only one term here that could change. Okay, so for the summation. So I know that's bad, but that's what happens when you do a lot of summation work. Okay, so we fit the model to minimize the sum of the residuals squared. And remember, right, we said that the residual is y minus y hat. Okay, I'm gonna add a page here, bump those down a little bit. Okay, and so yeah, but then the y hat is actually beta naught plus, or beta naught hat plus beta 1 hat x. So what we could do is we could rewrite this, expanding the brackets right away, y minus beta naught hat plus beta 1 hat. Oops, sorry. I said to expand the bracket and then I didn't. Minus beta 1 hat x. Okay. So really what we have is we say that, okay, the residual sums of squares, residual sum of squares, which is really the residual squared and then the sum, right? But it just sounds nicer if you call it the residual sum of squares, because then we can call it the RSS is the sum from I equals 1 to n. Now that I've pointed it out, I'll try to be more proper, but if I drop it off, then don't worry, it's still there. It's supposed to be there. It's just me being sloppy. Okay. But that means that you're allowed to be sloppy too. So now if I take this error term, the residual, and replace it, then we'll see what happens. We get the sum from I equals 1 to n of y minus beta naught hat minus beta 1 hat x squared. Okay, so really what's happening is we're trying to find the beta naught hat and the beta 1 hat that minimizes the residual sum of squares. So the RSS is that summation. Bump it closer. Okay. So what that means is that the least squares regression line, it selects a model that minimizes that has the coefficients that minimize the residual sum of squares. Now, for me, I always kind of have a hard time, and it is an iterative process, okay? So because we find the residuals by having a line, right? And then we can calculate the distances, so that's the residuals, but then we're also using the residuals to find the line. Kind of makes no sense, right? But if you kind of step back and think about it, it should make sense, right? And so the line that we land on, although there are many, many different ones, right? Arguably an infinite number, we land on the one that minimizes the RSS. Okay. Therefore, the least squares approach chooses beta naught hat and beta 1 hat to minimize the RSS. No. Now, what happens is we could use calculus, and we could, you know, this turns into a calculus problem. As soon as I want to minimize something, what do you have to do? Well, you'd have to take the derivative of the function, set it equal to 0, solve for the values that make that happen, right? And so we're not going to do that. I'm just going to give it to you. But just know that there is, you know, optimization going on in the background. As soon as we're trying to minimize, we're optimizing, right, to the smallest value. You could also optimize to the highest value, but no, not in this case, right? We want to minimize the residuals. So I will add that using calculus, we could find that beta 1 hat is the sum from I equals 1 to n of xi minus x bar times yi minus y bar divided by the sum from I equals 1 to n of xi minus x bar squared. Yeah, no using calculus. I promise. That's as close as I'll get to using calculus again for you guys. Maybe, unless we do it for the maximum likelihood, but then it's like really prescribed. I promise. Using calculus, we could find this. No, thank you. We're done with that. Okay, so this, or from stat 230, depending on how far you guys got, I haven't actually looked at the regression notes. I was more concerned with some other stuff, but So I can't remember how far you guys got, but that's okay. Usually we use B's in Stat 230. It's a little bit more, I don't know, easier to swallow at least. If we have y hat is b naught plus b1x, then b1 is r times the sx over sy, and b naught is y bar minus b1 x bar. Okay, we can work this out, and this actually becomes the same thing that we have here. Okay, so xi minus x bar, okay, and if I square that and then I add them all up, and then if I divide by n minus 1 and then I take the square root, then I have the standard deviation of the x's, right? So on and so forth. So you could work through and you could find the link between these, but they're doing the same thing. Okay. So this is actually a summary of this. Okay. We'd have to rework it a little bit, but don't worry about that, right? I just wanted to show you that you have probably seen something about this before. Okay, and so beta naught hat relies on beta 1 hat. Remember, you have to find the slope before you can find the intercept. And we use y bar minus beta 1 hat x bar. Okay. So good. We're not going to do that by hand. Obviously, we use software for pretty much everything, right? Because our data sets are yeah, totally. Here you had to skip the calculus, but it's easy enough. And then of course here, this is the same. Circled weird, but anyways. Okay. Yeah, so yeah, it always helps to remember, okay, it's not all weird. We have seen a lot of this stuff before, but we're seeing it in a weird way, in a theoretical way, right? And that's not fun, but I just wanted you to see that, okay, we do know what's going on here. Okay, so we won't be doing these calculations, right? So we don't do these calculations by hand. We let software do them. And most software will do it. Yeah, or I guess I shouldn't put a colon here. Right, and so we're not going to do these calculations by hand, but you could find all the different components and you could plug them into the formula, and that's fine. But what we need to do is we need to be able to get some output, and what's nice is getting this output is really quite simple, and so we'll see that on Friday, but it's interpreting the output. That's the important part, right? If you're an analyst, then you need to be able to interpret the output. So that's what I want to focus on today, because otherwise it just gets a little out of hand. And so most output gives you the standard errors as well as the estimates. Okay. So most output will produce the estimates. Which is beta naught hat and beta 1 hat, as well as the standard errors, because we know that this is just built on sample data. So if I were to collect a random sample again, and build a new model, we understand that the coefficients here, so these are the coefficients, they would change. So as a measure of variability on those coefficients, we need the standard error of those coefficients. So we'll produce the estimates as well as the standard errors of the estimates. Now, usually we call them SE hat, beta naught hat, for example. But then there's hats all over the place, or simply SE of beta naught hat, because then you can see that this is on the estimate. So of course there it's an estimate. Okay, that's just a little shorthand. Okay, so once we have the estimate and the standard error of those estimates, then we have a lot of tools that are available to us, right? We can find a test statistic, and it is just going to be a T for starters, okay? And then we can find things like, well, once we have a test statistic, we can find the p-value and we can draw conclusions, assuming we have some null value, right? And we can build confidence intervals, right? We can have some estimate plus minus some error bounds, which take into account the standard errors. Okay. So we can use the standard errors, or I'll say the estimates and their standard errors to find test statistics and confidence intervals for each of the coefficients. For each of the coefficients. Okay. So if you're doing a hypothesis test, for example, then we can calculate a test statistic T because we're using numerical data, right? So the T is still for numerical data. Z scores are for categorical data, typically. Okay, so T is a point estimate minus the null value, which is from the null hypothesis, over the standard error of the point estimate. Yeah. What we're testing here, the null hypothesis in this case, is that beta J, or maybe beta 1, we're only simple linear regression for now, beta 1 is equal to 0. Beta 1 is the slope. So this is really saying that the slope is not significantly different from 0. Think about what a slope of 0 means. Slope of 0 is something like this, right? So what that means is that there's no relationship between X and Y. It doesn't matter if X is 10 or if X is 400, the Y value is roughly the same, right? And so that means that there's no relationship there between X and Y. Okay. So here, if we have some Y value and we have some X value, then if you have a relationship like this, right, then here the slope is essentially 0, right? Because it doesn't matter if X is here or if X is here. The predicted value of Y is the same. Okay. So that's what it means to have a slope of 0. So what we're testing is actually, is there some relationship between X and Y? Right, and so the alternative hypothesis here would be that there is some relationship between X and Y, but the null hypothesis is that there is no relationship. And I'm trying to keep it on the same page, but I'm running out of room here. There's no relationship between X and Y. Okay. So we can, if we have an estimate for the slope, right? If we have a point estimate for the slope, then that's going to be your beta 1 hat minus the null value. The null value is that beta 1 equals 0. Okay, so the null value here is 0, which is from here. How far is my coefficient, my estimate, from 0? If it's significantly far enough from 0, taking into account the spread of the estimate, right, then I can conclude that, okay, well, there must be some relationship here. Okay? And then this standard error of the point estimate is the standard error of beta 1 hat. Okay. We could also do a confidence interval for the slope, right? And usually it's included in the output. So a lot of output will include the p-value for the test statistic or for the t-test, as well as a confidence interval, or you can just ask for it. So you can build a confidence interval, which is going to be a point estimate plus minus some critical value times the standard error of the point estimate. So all you really need is the point estimate and the spread of the point estimate in order to do hypothesis tests or confidence intervals or both. Okay? Critical values here, we can get really specific, but and what I don't like is that we spend so much time talking about, oh, well, 2.009 is actually really different from 1.96. Not really. So this textbook, I noticed and I appreciate, they just use 2. If you end up having to build a 95% confidence interval, they just stick with 2. And so I find that's really nice, because if we wanted something more precise, we should use software. Right. So here, for a 95% confidence interval, use a critical value equal to 2, right? If calculating by hand. Right? If you're using software, they're going to use the appropriate T-star with the appropriate degrees of freedom, and that's great. But if you have to get rough approximations, 2 is just fine. Okay. So let's have a look at some output here. So here, we're looking at the advertising data, okay? And we're given these coefficients. We're given a coefficient for the intercept, and we're given a coefficient for TV. Now, TV is the predictor variable, okay? And I'm trying to predict sales. right? The amount of sales that we have in thousands. If we spend some amount on the TV advertising. So notice here, we've got the coefficient, and this here is beta naught hat, and this is beta 1 hat. Yeah. Then we have the standard error of the intercept and of the slope. And so this is the standard error of beta naught hat, and this is the standard error of beta 1 hat. If you take 7.0325 minus 0, well, you're just left with what you have, and then divide by the standard error, 7.0325 divided by 0.4578, then I get T is 7.0325 divided by 0.4578. So that's where that 15.36 comes from. 3615, blah, 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 blah. Okay. If you have a T of 15, some odd, doesn't matter how small your sample size is, it's going to be significant, right? Because that's a really large T-score. And so, and here it's confirmed the p-value is less than 0.0001, right? So really, really small. Okay, good. So we can look at the individual intercept and the slopes, right? But we can also look at these as how they contribute to the model, right? And so it looks like here, both of them, especially the slope, is the one that we're most concerned about. Does having TV in there as a predictor, does that help in predicting the sales? It looks like it does because this p-value is really, really small, which means that even though the slope of 0.0475 is really small, right, in comparison, that slope is significantly different from 0. Okay? So that's good. So it means that there is a relationship between the sales and the TV budget. Yeah. So in terms of the slope and the intercept, right, the definitions, it doesn't hurt to talk about the definitions of the slope and the intercept, because it's not some secret. How do you interpret the slope and the intercept? What you do is you apply the definitions to these specific numbers, right, and to this specific data set. And so it's nothing crazy going on. You just need to bend the definition to match the data that you're talking about, right? And so the slope, we'll start with the slope, is the expected change in Y, or in the predicted value of Y, with a unit increase in X. So it's the expected change in the predicted value of Y. I'm a little bit redundant here, but I'm not going to worry too much about it because the predicted value is the expected value, but it's okay. The expected change in the predicted value of Y for each unit increase in X. So in terms of these coefficients here, right, it means that we expect to see an increase of 0.0475 in the predicted sales for each unit increase of $1,000 in the TV advertising budget. Yeah. We expect to see a 0.0475 unit increase in the sales oops. Right? But this is in thousands, just as a reminder, right? So before you publish, you would have to multiply it by 1,000. So it's $475 in the sales for each unit increase in TV advertising, which is the budget for the TV advertising. For each unit increase in the budget for TV advertising. Which is also, a unit is also in thousand. Or maybe it's $1,000. Okay, so you need to be able to take that definition and apply it to this scenario. Let me just check here. 475 times 1,000 is 4750. Sorry. They rounded to 50. It's 4750 equals there. Whereas the intercept, and it's implied that we're talking about the Y-intercept. The intercept is the predicted value of Y, when X is 0. When X is 0. Oops. So here, if we let the TV variable be 0, so we spend nothing, we budget nothing on TV advertising, we're still going to make sales, right? But we have already seen that the sales are going to increase for each unit of TV advertising that we add. But as a blank slate, we would still be expecting to make 7.0325, so 7,032.50. We expect to make, oops. And let me just double check. 7.0325 times 1,000. Yeah. To make 7,032.50 with no budget, or maybe I should say when the budget for TV advertising is 0. When the budget for TV advertising is 0. Okay. So what we can do is we can build the model, right? That we write out this model and it becomes Y hat. Y hat is 7.0325 plus 0.0475, I want to say. Keep thinking I have it there, 0.0475. Sometimes I'll put the TV, right? If it's a nice variable with a nice name like TV, then I use it. Sometimes I'll just use X. Okay. Good. So once we have a model that we can work with, let me add a page here, then we assess the model fit. Yeah. And you might remember things like R squared. We can also talk about the RSE, and now I'm trying to root squared error, I think. We just call it the RSE, so that's why I can't remember what it's called. But once we have a model, we assess the model fit. And this is true for any model, right? Once you have a model, then we need to assess the model fit. And then we use those values because you're likely going to build many models, right? And then you want some method of comparing those models, okay? So the model fit. Most commonly, we use, I feel like it's the root squared error or something, the RSE, which is the root of 1 over n minus 2 times the RSS. And the RSS is the residual sum of squareds, so it's the errors squared and then summed up, right? That depends on the values of y, right? So it depends on the units of y. So for that reason, we don't tend to use it as much. Okay, so caution, the values for RSE have the same units as y, right? So if y is in, you know, some huge unit, right? Then your RSE is also going to be in that huge unit. And then, so if we're comparing, let's say, you know, kilometers to centimeters, then we can't compare RSEs from kilometers to RSEs from centimeters because they're not the same thing, right? So the values for RSE have the same units as y, which means models with different values of y can't be compared using the RSE. Can't be compared using RSE. So instead, typically what we jump to in Stat 230 is we say, okay, we're just going to use the R squared. The R squared is a proportion, so that's nice because now we're between 0 and 1, and the proportion is going to behave the same way regardless of what units we're dealing with. So that's really nice. So instead, we use the R squared. Oh. Okay. R squared is the proportion of variability. Proportion of variability in y explained by the least squares regression line on x. That's a long blurb, but what you need to start latching onto is this proportion of variability. As soon as you hear proportion of variability or the proportion of variation or something like that, percentage of variability, right? Then you need to start thinking, okay, R squared, that's R squared, right? Maybe confirm, but as soon as you hear proportion of variability, I want your mind to go R squared, okay? So it's the proportion of variability in y explained by the least squares regression line on x. Okay. So a proportion is between 0 and 1, and so that's good. Now, we can talk about, as a formula, we can find R squared, and there's a couple of different ways that we could do it, but just as a side note, note R squared is actually the total sum of squareds minus the residual sum of squareds over the total sum of squares, where the total sum of squares is the sum of yi minus y bar squared. So it's really just seeing, okay, how far are my y's from the average, right? How much total spread in y do I have? And then I'm looking at those distances squared. But we're going to ignore that. It is something we can dive deeper into, but we don't really have time to do that, so we're going to skip it. Okay, but just know that we could use sums of squares to find the R squared. Okay. So one thing that we kind of struggle with is, what's a good value for R squared? Now, R squared, it depends on if we are actually looking at something that would follow a linear model. Okay. So if we want to answer what is a good value for R squared, oops. Well, it depends. Okay. It depends. If the population that we're pulling a sample from follows a linear model, then R squared should be really high. So if the population, all right, and I'll highlight that here, if the population follows a linear model, or has a linear relationship, I think of it as kind of truly linear, right? If there's some something that's truly linear. So in physics, you're dealing with these truly linear distributions. Like if you if you throw a ball, it goes some distance, and that depends exactly on all these different variables, right? And so then we have this truly linear relationship. I'm really bad at physics. I don't know. We've got some physics pros in here, so I don't know. I made up a bad example, I think, but for example, in physics, we have these perfectly straight line relationships, and so then we're expecting a really high R squared. So if we're pulling from a truly linear relationship, then we expect really high values of R squared, closer to 90%. Some people might cry if they get anything less than 90%, because they're so used to seeing these high R squared values. And then you go to biology, and biology, they're jumping for joy if they get an R squared of 30%. We win. So it totally depends on what population you're pulling from. Okay, so if the population has a linear relationship, we expect a very high R squared value. Oops. Okay, kind of 90%-ish. Okay. If the population is not linear, and we're trying to approximate it with a linear model, then we expect kind of a low R squared. We can do that. We should try to find better models, but a lot of the time we don't know what a better model would be. And so if the population right? And we don't know what the population looks like. That's the problem. That's our whole goal, trying to learn about the population. So if the population is just kind of is not, maybe I'll say it is only approximately linear. How about that? Because if it's completely non-linear, we need other tools to deal with that. But sometimes we've got these kind of relationships that are, you know, sure, we're going to use a straight line here. So if the population is only approximately linear, we expect the lower values of R squared. It hurts, but maybe I'll say 60% or something. Totally depends on what field you're in, and you'll pick up very quickly once you're out working what a good R squared is in your field, right? So don't worry, but just know that it can fluctuate, and it depends on what population you're drawing from. Okay, so in simple linear regression, the R squared value is the correlation squared. Okay. It only works for one predictor. So only if you have one X, one predictor or X value. Okay. So for example, here, we've got some output that goes with this model that we were looking at, right? So this is the output here. And along with that output, we're going to get a bunch of other information as well. And so some of that information here is the residual standard, residual standard error. I know, something like that. Can't remember what I called it, but anyways, it's the residual standard error. And maybe I'll add that in here. Residual standard error. Okay. 3.26. Now 3.26 depends on the value or the units of Y, which is in thousands of dollars. Right? So the residual standard error is $3,260. Okay, that doesn't really do anything unless we're comparing different models, right? So the R squared in this case is 0.612. And so what that tells me is that, okay, this linear model, it does a decent job, right? It could be because it could be low because the population is not truly linear, right? Or maybe I'm missing some predictors, right? Maybe there are other pieces of information that I need to incorporate into my model to make it better. It also includes the app statistic, which we haven't talked about yet. And we use it as soon as we have more than one predictor. So we can do it for one predictor, but usually we ignore it until we have two. Okay. Uh-oh. I've done it again. I've managed to blab my way out of time. Well, not really. It's just I wanted to start a whole new section, and I will. But I know. Sorry. Sorry. Okay. So I just want to introduce multiple linear regression. Okay, and so multiple linear regression is section 3.2. although we can have more than 2 X variables, more than 2 predictors, it becomes really hard to visualize. Okay, and so for visualizing, we stick to 2 predictors. Okay, arguably impossible. You could incorporate, so you could have 3 predictors, but I'll show you what happens in a little bit here. So, or not in a little bit, we end in 3 minutes, but in a little bit. So multiple linear regression means that we have more than one predictor. So now we're going to have some x1, x2, x3, all the way up to, we're going to call it xp, where p, again, is the number of predictors. I only mention that because there are some restrictions on how many p's we can have, or at least what tools we can apply when p is large and that kind of thing. So, so that's good. So one thing to note is that we can visualize relationships when p equals 2. Okay, and what that's going to look like is it's going to look something like this guy. Right, so here we have x1, x2, and then I have the response variable here, right? But now we have this plane, this x, y, z kind of 3D model here, right? And now we have this plane instead of a straight line, right? We see a plane instead of a straight line. But I will highlight that it is a straight plane, right? And so it's still linear, right? But it's a linear plane. So we've got this kind of slice, and we can still find residuals, and so we can still use those tools that we introduced to build the models, right? But it becomes kind of hard to think about. So as soon as you have more than 2 predictors, we can't draw that anymore. It still works, right? But it's hard because we can't draw it. And so I'll leave that there, and we'll keep talking about multiple linear regression next day. If you have any questions, let me know. Otherwise, I'll see you on Thursday.